as last class we discovered from the crushed can demo, there's no such thing as a pulling force. There's no such thing as suction. There are only pushing forces. Because there are only pushing forces, there is no such thing as suction. That's because a vacuum is nothing. And if a vacuum is nothing, nothing does nothing. And if nothing does nothing, and a vacuum is nothing, and a vacuum sucks, suction is nothing. A lot of train of logic to go along with this. When you look at this image that we have here, you can see a couple of different things. We can see here on the left that before you put your mouth on the straw, that air, the weight of all that atmosphere, which we discovered in a 1 meter squared column, is 10,300 kilograms, otherwise 20,000 pounds. All that weight sitting on this liquid, both through the straw and on the sides of the straw. When you put your mouth on the straw, what you are doing is you are removing the air. When you remove the air and you decrease the pressure, the weight of the atmosphere pushes on the liquid. The liquid can actually go somewhere now. It can go up the straw, and that's how liquid's drawn up a straw. And you may ask yourself, well, wait, I thought I sucked air in with my lungs, and that is not true. Your diaphragm drops, and when your diaphragm drops, you increase the volume of your lungs. What I'm going to do is I am going to go to Scuba Steve to explore how lungs work. I'm going to do 2 pumps of gas. When I do these 2 pumps of gas and the molecules distribute themselves fairly evenly throughout that container, what I'm going to do is I'm going to decrease the size of the container for a second. Now what I want us to do is I want us to look at the pressure. Look at where that gauge is at, this gauge right here. Now I'm going to use my diaphragm and expand my lungs to bring in air. So watch what happens to the pressure gauge when I increase the size of my lung. Did you guys see the pressure going down? That's because there's more space for those molecules to move around. So they're striking the edge of the container, and the edge of the container has a greater area. Pressure is force over area. I made the area bigger, therefore I decrease the pressure because those two things are in inverse relationship. So when we go to the gas thing, when you make your lungs bigger, you drop the pressure in your lungs. That's how air at a higher pressure comes rushing in. You do not suck air into your lungs. Air gets pushed into your lungs from the pressure of all of the air on top of us on this planet. Try doing it in outer space. It's not going to happen. There's no air. In fact, you'll just pop, but we'll talk about that later. The weight of the atmosphere is strong. It's heavy. Hence this oil tanker crushed by the weight of the atmosphere because there was nothing on the inside of the oil tanker to resist the pressure of the atmosphere. This is an example, a real-world example, of the can crush that we saw happen last class. Atmospheric pressure, we saw this animation, and it was part of your homework assignment, the lab even more gas laws and properties, where you had to talk about pressure being force divided by area. All right. When you look at a graph of how pressure changes as you go up in the atmosphere, this is data collected by a weather balloon. If you see the green line, you see that the pressure decreases, decreases, and decreases as you go higher and higher in altitude. Some things actually increase as you go up in altitude, and that blue line is showing the ozone that's in our atmosphere. It's not in the layer of the atmosphere that we breathe air in, it's higher than us. And what that does is it causes the temperature. Believe it or not, the temperature of air, it decreases, then it increases again because of that ozone. We're going to move on. Pressure imbalances can lead to pain in your ears. Of course, most all of us have experienced going up a mountain and down a mountain because we live in Colorado, and your ears have to pop because of the elevation change. And that's, of course, due to a pressure imbalance. And again, like we said before, pressure is force over area, the force of the molecule striking an area. If I decrease the area, I make the pressure bigger. If I increase the area, pressure gets smaller. Make sure you know the relationship. A barometer is a device that we use to measure atmospheric pressure. You can look and study this and click pause on the podcast to learn about that more later. And then, of course, a manometer is what we built with those U-tubes when we built the glass. Manometers are used to measure the pressure of a contained gas. Make sure you know the difference between a barometer and a manometer. Moving forward, units of pressure. I want you guys to pause and I want you to look at the units that are on the back of your periodic table. Could you guys right now take out your periodic table and look in the back on the reference sheet, please? Okay, going back to our PowerPoint and what we were looking at. So units of pressure include torrs, atmospheres, millimeters, mercury, and you should be able to convert between each of them using dimensional analysis, where you go times fraction, units on bottom are what I want to cancel out, units on top are what I want to go to. Moving on, kinetic molecular theory. You guys have heard this before. We've had questions on this. The kinetic molecular theory essentially says that you have particles in constant motion. Kinetic means motion, molecular means molecule, and it's the theory that molecules are always moving. And essentially that they will fill up the space of their container using their energy, and also that if you increase the energy, they move faster. Now, the gas law simulation applet was part of your homework assignment, and the homework assignment was dealing with Scuba Steve. Make sure you know how pressure, volume, and temperature are related to each other. That if I decrease the volume, the pressure goes up. If I increase the increase the temperature of my container, then what will happen? The volume will get bigger. And if I decrease the temperature of my container, the temperature goes down, then my volume should go down. When I'm decreasing the temperature and the volume gets smaller, that's of course a direct relationship. Make sure you know the difference between a direct and an inverse relationship. Let's go to looking at some basic properties of gases. Gases are compressible, much more so than liquids and solids. That's why when I go mountain biking, the shocks on my mountain bike are filled with air, not with a liquid or a solid. Gases are fluids. Remember, we're in a giant swimming pool at all times. The swimming pool is our atmosphere. They flow just like liquids do. Gases always fill the shape of their container, and they have low density. So if I took this liquid in this soda can and I boiled it into a gas, that gas would fill up 1,700 cans of soda. They take up a lot more space because of their densities in comparison to liquids. Gas laws. You guys took notes on gas laws from the simulations when you went on my website. Boyle's is a pressure-volume inverse relationship. Charles' volume temperature direct relationship. Gay-Lussac's pressure temperature direct relationship. Avogadro's moles and volume direct relationship. And the combined gas law is an equation which relates pressure, volume, and temperature. You do not need to memorize the names. But if I tell you you increase the pressure, you should know that the volume decreases. Think of a stuffed animal, and you increase the pressure and you squeeze the stuffed animal, it gets smaller. We're going to look at some examples of each of them. Boyle's law, increase the pressure, volume gets smaller. You don't need to know the name, but you do need to know the relationship between the two of them. You saw this animation, of course, from the assignment, even more gas laws and properties. Moving on. Classic example of this is that you can increase the pressure of your tires. How are you doing that? You are decreasing the volume in the container of your bicycle pump. That's how you increase the pressure. You should have looked at this one as well, and the even more gas laws and properties. And if you plotted data, you would have seen that it is this inverse relationship like we saw on the gas properties simulation. Now I want you guys to think about how you get high when you go scuba diving. You may be like, high? How do you get high? Well, what happens is when you go to deeper depths, there's more pressure on you. When you're near the surface, there's less pressure on you. Nitrogen is most of air. That's about 77% of what you breathe is nitrogen. Nitrogen, under low pressures, doesn't dissolve in your blood, but under high pressures, it does dissolve in your blood. When nitrogen dissolves in your blood, you get high. Unfortunately, if you rise too fast when you're scuba diving, all that nitrogen comes out of your blood too fast, and you get big bubbles coming out of your blood vessels. That's a bad thing. What does that do? It pops your blood vessels, and you can die from that, and that's called a condition called the bend. So if you rise too quickly when you're under pressure, then you have to be in a hyperbolic chamber where they keep you and slowly let off the pressure over time so that the nitrogen gas in your blood doesn't boil out. Boiling blood's a bad thing. I think that's the point of my lesson. So, here's Mr. Burt Swimming. What I want you guys to do is tell me why this is not going to work. Someone raise their hand and explain for me why this is just a really, really dumb idea. Anyone? Think about it for a second. Matt?
Because you can't suck. You can't like suck.
You can't suck, you're right. All you can do is expand the volume in your lungs. Guys, how many of you have swum to the bottom of a deep swimming pool before, holding your breath? Yeah, when you do that, do you feel the pressure, the weight of all the water on top of you? That's a very noticeable pressure difference. Is it easy to move your lungs out when you're under that deep pressure? No. Why? Because if you can't make your lungs bigger, The weight of the atmosphere can't push all the air down to fill your lungs in. That's why in old Popeye cartoons where he's scuba diving, they've got guys on a boat and they're going back and forth with a pump. They're pressurizing the air to get into your lungs. The air has to be at a higher pressure to push the air into your lungs so that you can breathe. Try it. Try taking a reed. Try taking a hose. Actually, this is a bad idea. I'm going to kill one of you guys. Yeah, try taking a hose, like a garden hose, and go in the bottom of the swimming pool and try breathing. It's not going to work. You'll be you can't suck the air. You can't suck the air in because there's no such thing as suction. Remember, the air has to push its way down, and the weight of our atmosphere is not great enough to push the pressure high enough down the hose. That's why we have to pressurize gases when you go scuba diving. That's what the tanks are, compressed air. Yes.
So then, how does it work with oxygen tanks? Because there's still that pressure from the water, isn't it?
Yeah, they're pressurized. That's why when you see a scuba diver and you see their tank, that's pressurized air. It's at a high pressure. When the pressure drops too low, then you can't breathe anymore, and that's why you got to constantly look at your pressure gauge when you're going scuba diving. My wife's a huge scuba diver. I'm not. I don't like going deep depths. Which balloon's going to get bigger, guys? The top one or the bottom one? Top one, yeah, because the pressure of the water will squeeze the balloon. Top one's going to get bigger. Very good. Let's move on. Charles' law, direct relationship between temperature and volume. Of course, you boil water, you're going to cause these particles to move faster, and they're going to expand the balloon. And that's how hot air balloons work. That's why you have that burner in a hot air balloon to increase the temperature of those particles, and they expand, and then the density becomes lower inside the air balloon than surrounding it. Charles' law's direct relationship. We talked about these graphs before. Avogadro's law is a direct relationship between the number of moles. You guys want to see an example of Avogadro's law? It's the coolest demo I can do. You guys ready to see Avogadro's law? You ready? 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 This is disgusting. This balloon's probably been touched by someone. So let me rinse off this balloon before I do it. Here's Avogadro's law. You ready? So right now there's not that many moles of gas in here, right? I'm going to increase the number of moles. So I'm going to increase what's on the x-axis. Here we go. So as I increase the moles of gas in this balloon, the volume got bigger. What's going to happen to the volume if I decrease the moles? That's Avogadro's law. Most of these laws are kind of stupid. So make sure you know all of the gas laws in terms of what happens to the variables, but you don't need to memorize the names, Boyle's, Charles, Gay-Lussac's, Avogadro's. Only chemistry teachers have memorized them. You guys do not need to memorize them. Moving on. Now there's one called the ideal gas law. The ideal gas law, we're actually going to have to write some stuff down about how to use it. So what I want you guys to do is I want you to take out, okay, now that you've written PV equals nRT on your blank piece of paper, what we're going to do is look at the variables that are involved in it. P, of course, is pressure. The unit that we like to use for pressure is, of course, atmospheres. Liters, V is volume, and we always like to use liters. N is number of moles, and of course the unit is moles. T is temperature, and for all gas laws, it's always going to be Kelvin, and of course the unit that you use for Kelvin is just a K, okay? The R is something we call the gas law constant. And the gas law constant, there's actually two different types of units that you can use. We're going to be using one. It's a number that you can actually look up in your textbook. I don't think it's on your formula sheet. Let me check. It may not be on there. It's something I will give you during an actual test. Yeah, it's not on your formula sheet, unfortunately. The ideal gas law is on your formula sheet. R is a constant, meaning it never changes. The number is always going to be the same. All right, now what we're going to do is use the ideal gas law to be able to figure out why Mr. Bird can't breathe underwater. So we got PV equals nRT. So if something is on the same side of the equation, see how we have P and V next to each other on the same side of the equation? That's something we call, if they're on the same side, we call it an inverse relationship. If the two variables are on opposite sides, then it is what we call a direct relationship. So we know pressure versus volume is an inverse relationship. That means if I increase the pressure, my volume goes down. So if the pressure of the ocean is squeezing Mr. Bird's lungs swimming underwater, the space of his lungs are smaller. He's getting smaller, just like that balloon was in the example. Do you guys have any questions about that?